Hey guys, hi. So in this video, we will see the questions of JEST 2012, and all the questions will be of solid state physics. And eventually, we will see all the questions of all other years. So let's start with the first question. So here it is said, a beam of X-rays is incident on a BCC crystal. If the difference between the incident and scattered wave vector is k is equals to nx cap plus ky cap plus lz cap, where the x, y, and z cap are the unit vectors of the associated cubic lattice, the necessary condition for the scattered beam to give a Lay maximum is. So the question is actually very direct. Here the wave vector is given to you. You're having a X-ray which is incident on a BCC crystal, and difference between the incident and scattered wavelength wave vector it is given to you. Here x, y, and z. These are unit vectors which is associated with the lattice. So you just ask the necessary condition for the scattered beam to give a Lay maximum. So this is actually a theory-based question. So wave vector k is given to you, and x cap plus ky cap plus lz. So if you talk about the BCC crystal, you know for BCC crystal, it is a direct question. Okay, it is, you know, that h plus k plus l. Okay, it should be even. Okay, it should be even. Sometimes you might be given some different values, so you will have to check. In that case, you will go for those values which is giving you the sum to be even. So this is very easy. You can write the option 8 with the correct option directly. Clear? So these questions are actually in this 2012. The questions are very direct. These are not tough. This is just based on the theory. So we will see the next question here. Here is said the second order maximum in the difference of X-rays of 0.20 nanometer. The wavelength from a simple cubic crystal is found to occur at an angle of 30 degrees to the crystal plane. The distance between the lattice plane is here. So here the second order maximum. Which order? Second order maximum. In the diffraction of X-rays, wavelength is given to you 0.20 nanometer. It is for a simple cubic length. Okay, cubic crystal, SNC crystal. So it is found to occur at an angle of how much? 30 degrees. So crystal plane, angle with the crystal plane, it is given to you 30 degrees. You are just asked to calculate the distance. Distance means small d. So you know the Bragg's law, d sine theta is equals to what? N lambda. You know here d is the distance, theta is the angle, right? Which is occurring to the crystal plane. N is the order and lambda is the wavelength. So directly we will put the values. D is as it is. Sine 30 degree is given to you. Okay. We are dealing with the second order, so it is 2. If it would be third order, N would be 3. Okay. And lambda is what? 0.20 nanometer. So for nanometer, you will have 10 to the power minus 9. So D, you know, sine 30 value is what? 1 by 2, right? So this is 2 into 0.20 into 10 to the power minus 9. So clearly you can write D is equals to what? This 2 will come to the right hand side. It will be 2 to the 4, 4 to the 8, and with a decimal, right? This 10 to the power minus 9. So you can directly write what? D is equals to 8 into 10 to the power minus 10. Because the answer is in Armstrong, we will write it as 8 Armstrong. Clear? So this is the distance. So what you have done, you have directly used the Bragg's law, right? This is the Bragg's law. So questions are very direct. Now let's see the third question. This is the last question which came in 2012. So here it is said the Dulong patate fails near room temperature 300 Kelvin for many light elements such as boron and beryllium because their Debye temperature is. So this is one of the limitation of Dulong patate. Okay. So here it is said it is failing near the room temperature, that is 300 Kelvin. For many light elements, the elements given here is boron and beryllium. Why does it fail? This is what you need to tell. So if you have studied the theory part, you will know that for boron and for beryllium, okay, for both of them, the Debye temperature is what? For boron, it is 4180 Kelvin. This is approximate values. Remember, these are approximate values, and this is 4181 Kelvin. So if you see this is 4180, this is 4181. Okay. So if you say this will fail because you already need to say the Dulong patate fails near room temperatures. So these temperatures, this is Debye temperatures, these are Debye temperature, all right? So these temperatures, if you see, these are very, very greater than 300 Kelvin. Okay, so this is the reason that the Dulong patate law, it fails for light elements, okay, such as boron and beryllium. Why? Because 4180 and 4181 Kelvin. Okay, These are what? Very, very greater than 300 Kelvin. Clear? So your answer is option A. So this is it in this 2000 year questions. So the questions are very easy. If you have any problem, you can just go to the theory part and study. Okay. Okay. So if you are having any problem, then just go to the Dulong Packet. You can get it in any book or Google, wherever. You can see the limitations, and there you'll get this points. So that's all in this video. Thank you so much. Next, we will do 2013, 14, and all other 2022. Okay. Have a good day.